Hi, everybody. So we have a temporary setup for today before we go back to our usual setup. So you should be looking at a Zoom, and you should be looking at an echo as well. All right, so remember that tomorrow there is no lecture, but I will be posting a makeup lecture, and be looking for that on the on Blackboard. All right, so last time we were talking about halohydrin formation as our new reaction. And so let's just recap that. Recap of halohydrin formation. Yeah. All right, so in that reaction, we had a alkene reacted this with molecular halogen in the presence of water, and that double bond is degraded to a single bond, and X adds at one end of where the double bond used to be, and OH adds at the other end of where that double bond used to be. And we remember that we said about this reaction that we had, it's a trans addition. In other words, the X is on a dash and the OH is on a wedge, or the X is on top of the molecule, the OH is on the bottom of the molecule. And this involves a cyclic halonium intermediate, not a carbocation, so there aren't any rearrangements. And another thing that we remember, cyclic halonium on the less hindered side of the original alkene. And finally, that OH is on the more, this should say C double bond C, OH on more substituted carbon. Okay, so that's what we were talking about when we called time last time. Okay, so now I want to talk about variations to this reaction. And first important variation to talk about is that we can have an intramolecular reaction if a 5-membered ring or a 6-ring can form. Remember when we were talking about strain, we pointed out that the 5-membered ring and the 6-membered ring, these are the least strained of the rings. So when one of these rings can form, we're going to get this halohydrin reaction is going to give us a 5-membered ring or a 6-membered ring. Okay, so an example would be something like this. If we react this with Br2, what's going to happen? Well, first of all, we will get the attack of the double bond on Br2, and we'll get that cyclic halonium intermediate, right? That little triangle that is tipped by Br+, And now the cyclic halonium is quite strained. It's dying to be busted open by a nucleophile. But the nucleophile, in this case, is on the same molecule that the double bond was. So the reaction is not intermolecular. It's not the reaction of two molecules, two discrete molecules coming together, but rather the electrophile and the nucleophile are on the same molecule. And I see the possibility of forming a 5-membered ring or a 6-membered ring, excuse me, which are the most thermodynamically stable kinds of rings. So this oxygen has unshared electron pairs. It's the nucleophile. It's going to bust open the cyclic bromonium ion by attacking the More substituted carbon. So this carbon here, that's primary. This carbon here is more than primary, it's secondary. And when I hook up this oxygen atom to this More substituted carbon, I'm going to get a 1, 2, 3, 4, 5-membered ring. And so that's thermodynamically favorable. So that oxygen atom attacks this carbon. It flings the carbon-bromine bond open. I get a 5-membered ring. And that H on that oxygen atom is still hanging on for dear life. And let's see, 1, 2, 3, 4, 5, CH2, 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 CH2. So I have this little bromomethyl tail there. And now the Br minus comes in, functioning as a base. It picks off this proton. The oxygen atom absorbs that electron pair that used to be holding that hydrogen, that proton there. And so we get this as the final product. Okay, so that's an example of an intramolecular halohydrin reaction. The important thing here is that the cyclic halonium ion and the nucleophile are on the same molecule. And I see the possibility of forming a 5-membered ring or a 6-membered ring. Okay, so let's build on this and let's do a more complicated problem. So it's a stop sign. It's a stop sign with nitrogen at one end. It's an 8-membered ring. It's a stop sign. 1, 2, 3, 4, 5, 6, 7, 8, and back again. And I have a double bond over here. And now I'm going to react that with I2. And what is going to happen? Okay, so I see the ingredients for that intramolecular halohydrin. All right, so let me see. Is there something instructive here in the chat? Could I quickly go back? Well, this thing? Okay, so, all right, so that's it. All right, so what is going to happen here is, first of all, that double bond is going to attack the molecular iodine, and we'll get I minus swimming around in the solution. And so we see the formation of that, it's a stop sign. There's the cyclic iodonium ion. But now this nitrogen atom in this molecule, that's a nucleophile because it has this unshared pair of electrons on it. And so the nucleophile and the electrophile are on the same molecule. And so it's going to be a rapid intramolecular reaction. But that nitrogen atom is going to attack the More substituted carbon. This carbon is secondary, this carbon is secondary. So we have a crisis now. We don't really, we can't tell what is going to be attacked based on the degree of substitution, but we can tell which carbon is going to be attacked based on the possibility of forming a 5-membered ring or a 6-membered ring. So if this nitrogen atom attacks this carbon here, this carbon here at around 130, we're going to get a 1, 2, 3, 4-membered ring. That's no good. And if this nitrogen attacks the carbon down below, we're going to get a 1, 2, 3, 4, 5-membered ring. Okay, that's good. That's thermodynamically favorable. So this nitrogen attacks this carbon, flinging the carbon-iodine bond open. And so again, drawing this thing, trying to draw this as a stop sign, 8-membered ring. This nitrogen has now attacked that carbon there, and the carbon-iodine bond has been flung open. We get something like that. Don't forget charges, the formal charges here. This guy is positively charged. One of the things we believe in is charge conservation. So the intermediate there must also be charged. Now, I'm getting a lot of stuff here in the chat. It's very inconvenient for me to look at the chat because of my setup. So if you send me something in the chat and I don't respond, it's because I have to walk half a mile to where I have the Zoom set up. So forgive me for that. If you send me a chat message and I don't respond, it's because I'm nowhere near my computer, right? This is a temporary setup. Please bear with me. Okay, so now this is an ugly drawing. Let's try to fix it. 1, 2, 3, 4, 5, and back again. That's a 5-membered ring. 1, 2, 3, 4, 5. That's a 5-membered ring. So this is the very same as a 5-membered ring like so. Another 5-membered ring like so, and they are sharing this side here. And so I'm going to have nitrogen, put nitrogen there. And with that proton still hanging on for dear life with a positive charge over there. And the iodine is now down here. Wow. So that's a very big transformation. And now the I minus comes in, functioning as a base, removes that proton, and this electron pair collapses in on that nitrogen because nitrogen is quite an electronegative atom. It doesn't like to have that positive charge on it. And so that will be our final product. So we see that these intramolecular reactions, it's reorganization of the carbon skeleton, but it's not a carbocation mechanism that is involved here. Rather, it's one of these intramolecular halohydrin style reactions where we have the cyclic halonium ion, which is the electrophile, and the nucleophile in the same molecule, and we see the possibility of forming a 5-membered ring or a 6-membered ring. Okay, so more variations. Another variation to this reaction would be switching out the water for other nucleophiles. Replace H2O with other nucleophiles. Okay, so water, remember water is HOH, but we could replace water as the nucleophile with an alcohol, let's say, right? So something like that. Instead of HOH, we have HOR, where what we've done is replace the second hydrogen the water molecule with an organic group. So this could also be a nucleophile. This oxygen has unshared electron pairs, and so that could also be a function as a nucleophile. All right, and then we could also, as we just saw, we could replace the water with another nucleophilic species, and that would be a carboxylic acid. So again, water is HOH. What I've done is I've replaced the second proton of the water molecule with now this organic group over here. That's a carboxylic acid. Another thing that I could do is replace out the water with an amine, right? We just saw an example of that. So instead of water, now we have a nucleophilic nitrogen atom functioning as an as the nucleophile. Okay, so let's do some product prediction problems, shall we? What about something like this? And now we're going to react this with methanol and Cl2. So let's draw the structure of the product. What are we going to get? So it's a variation of the halohydrin mechanism. So what happens first is the attack of the double bond on the Cl2. We get this cyclic chloronium ion. And now instead of water coming in functioning as the nucleophile, we have this molecule of methanol. And so methanol is going to attack, it's going to use that oxygen atom as the nucleophile. It's going to attack the more substituted carbon, and it's going to break this bond to the Cl, and we get the oxygen has broken open that cyclic chloronium ion, and notice that proton on that alcohol molecule is still hanging on for dear life. It is removed finally and at last by Cl minus, which functions as a base, coming in to remove that proton. So we get HCl, and the final product here is going to be, that. Okay. So now how about let's try another product prediction problem, but this time let's combine the intramolecular reaction with this new kinds of nucleophiles. All right, so what about something like this? Let's draw the structure of the product there. So it's the recipe for a halohydrin type of reaction. I see the carbon-carbon double bond, and elsewhere in the molecule, I see a nucleophilic oxygen atom. So if you, in the basic, in the most fundamental expression of this reaction, this would be water. But now this oxygen atom is bonded to a proton on one side and the rest of the organic molecule on the other side. So the product of this reaction would be, okay, let's just go through this mechanism one last time. So we have the double bond attacks the iodine, we get the cyclic iodonium cation. And now the nucleophile is going to be the oxygen of the carboxylic acid, this OH oxygen of the carboxylic acid. And can I form a 5-membered ring or a 6-membered ring if I attack the more substituted carbon? So this carbon here is secondary, this one is primary. 1, 2, 3, 4, 5. Yep, when I hook up that oxygen atom with the more substituted carbon, I see the possibility of forming a 5-membered ring. So this is going to attack here, flinging this carbon iodine bond open like that. Okay, so now try to draw in a decent way, put my dimethyl up there. Then I have CH2, and then I have my carbonyl oxygen, and then I have the attacking oxygen atom with that proton still clinging for dear life, and it attacked this carbon here. And so I have this iodomethyl tail, like so. And now the I- comes in functioning as a base, removes this proton. And so my final product is going to look like this with this iodomethyl tail. Okay, so that is the halohydrid family of reactions. Now it's time to go on to the next reaction, which is going to be the acid-catalyzed hydration. Acid-catalyzed hydration of an alkene. All right, the overall reaction here is going to be you're starting with an alkene. You add water, right? Hydration means adding water. Many people are obsessed with their state of hydration. And so if you're worried about that, you're going to drink water. And then there is, the reaction is catalyzed by acid. So that's a proton. And this guy is usually, but it doesn't have to be, it's usually from sulfuric acid, H2SO4. But sulfuric acid just dissociates into HSO4 minus and the H plus. So sometimes you'll see H2SO4, but sometimes you'll just see H plus. And this reaction requires boiling, right? It's not an easy reaction to carry out. So it has to be, the reaction mixture has to be boiled for sometimes for a considerable length of time. And anyway, what is going to happen here is that that double bond is degraded to a single bond, and the elements of water add across where the double bond used to be. So this is a way of making an alcohol from an alkene. All right, so bullet points for the reaction is we have the new OH on the more substituted carbon of the original carbon-carbon double bond. So in other words, we're talking about Markovnikov regioselectivity. And we're about to see that this is a carbocation mechanism. And so that means, whenever we talk about carbocations, rearrangements have to be considered. So this is a carbocation mechanism, and rearrangement is possible if we can go from a less stable carbocation to a more stable carbocation. And the reaction is also stereo random, meaning that the carbocation intermediate can be attacked from, let's just put this in quotes, from above or below with about equal probability. Remember, the carbocation is sp2 hybridized and it's planar. And so once the carbocation forms, it's possible for it to be attacked from above or from below with more or less equal probability. Now, this acid-catalyzed hydration reaction is of huge importance industrially, but because of these forcing tough conditions, sulfuric acid and boiling water, well, a lot of organic molecules won't survive those. But this reaction is very important industrially. So if you take crude oil, one of the things that you get out of crude oil or from natural gas could be ethylene. All right, so that's from crude oil. And we add water, cheap and abundant. We add sulfuric acid, cheap and abundant. Heat it. And what will we get? Well, the double bond gets knocked out. It's degraded to a single bond. And the elements of water add across where the double bond used to be. We get this alcohol. So this is ethanol, right? This is the alcohol that is found in alcoholic beverages, but this is not the reaction that is used in the manufacture of vodka or whiskey, right? This is for the creation of industrial grade, industrial use ethanol. And this reaction here is worth about $10 billion per year, right? And so it's a very, very important industrial reaction. Okay, but as I said, in the organic chemistry laboratory, acid catalyzed hydration only has limited applicability because of the forcing conditions of the reaction. Okay, so let's go through a simple mechanism and then let's go through something that's going to be a lot more complicated. All right, so something like this, methyl cyclohexene. I'm talking about mechanism. Methyl cyclohexene plus water plus sulfuric acid plus heat. What is going to be the product? Well, we're going to get the, okay, I'm going to put a methyl over here on a wedge. So the product here is going to be, that double bond gets knocked out, and I'm going to get OH at one end of where the double bond used to be, H at the other end of where the double bond used to be, and the OH is going to end up on the More substituted carbon. But because the reaction is stereo-random, because it goes through a planar carbocation that can be attacked from the top or from the bottom with more or less equal probability, I'm going to get two products here. One of them is the result of attack on the More substituted carbon from the front. The other product is going to be the result of the attack from the back. Okay, so that's what we'll go through the mechanism, but before we do that, tell me in the chat here, I've moved over here across the classroom, tell me in the chat how those two products are related? Are they constitutional isomers? Are they enantiomers? Are they diastereomers? What are they? Right, so we get two products. One of them, the OH comes in from the front. The other one, the OH comes in from the back. What are they? Are they constitutional isomers? Are they enantiomers? Or are they diastereomers? Oh, okay, well, good. Yeah, they are diastereomers. And remember that diastereomers are totally different compounds with totally different properties. They're going to have different solubilities, different IR and NMR spectra, different RFs in a chromatography experiment at different melting points, boiling points. They're totally different compounds. But if I change up the starting material by a little bit, see, if I got rid of that methyl group on the wedge, if I just went with that, very same conditions, water, H2SO4, heat, I'm going to get attack from the front. I'm going to get attack from the back. Okay, so now look at these two structures and tell me, how are they related? Yeah, tell me here in the chat. How are these related? Are they enantiomers, diastereomers, constitutional isomers? How are they related? Oh, they are identical structures, right? They're not enantiomers because enantiomers have opposite absolute configurations at all the chirality centers. And how many chirality centers in this molecule? There aren't any. The clockwise road into this carbon here is the same as the counterclockwise road, right? So no chirality centers here. These are identical structures. So depending on the structure of the starting material, of the starting alkene, I could get enantiomers, I could get diastereomers, I could get identical structures. All right, so let's go through a simple example of the mechanism, and then let's move into something that's more complicated. All right, so here, the first step is going to be the protonation of that carbon-carbon double bond by the sulfuric acid. So this is nothing new. We saw this in the reaction of an alkene with HCl, HBr, and HI. The first step was protonation of the carbon-carbon double bond. But it happens with Markovnikov regioselectivity. In other words, the most stable carbocation is formed. And so in this case, it's going to be this tertiary carbocation. Okay, and now the water comes in. And notice it is an intact water molecule. It's not OH minus attacking. It can't be. You have sulfuric acid around. That's an acid. OH minus is a base, a strong base. Strong acid like sulfuric acid and strong base like OH minus cannot coexist. So it's not OH minus that attacks. It is water that attacks. And so this carbocation can be attacked either from the front or from the back, and in this case, with equal probability. So just draw them out for the record. So here, the water molecule attacked from the front, the intact water molecule attacked from the front, and the intact water molecule attacked from the back, to form this oxonium ion. And now there is a deprotonation of that oxygen atom. Is some base comes along and removes that proton. And I have some comments about what that base is in a second. minus H plus, minus H plus. All right, and there's the mechanism for the formation of what looks like two identical structures. I'm just trying to communicate that the carbocation can be attacked from the front or from the back, but the stereochemical outcome of the reaction depends on what the starting material is. Okay, so I have some comments about this step here, this final deprotonation. The way I've written it, it looks like the proton is just falling off of its own accord, but that's not really what's happening. What's happening is a base is coming along and removing the proton. So actually what is happening, I'm just going to annotate it here, is that some base comes along and removes this proton. Some base comes along and removes that proton, but we don't know exactly what that base is, or rather we have many candidates for that base. In sulfuric acid, you'll have H plus, but you'll also have some HSO4 minus. That could have been the base that removed that proton. Water also functions as a base. So that could be the base that removes that proton. Look at the first step of the mechanism. The first step of the mechanism was a carbon-carbon double bond, and alkene picked off a proton. Well, the carbon-carbon double bond, that could also be the base. So instead of committing to writing what that base is that removes that proton, I just like to write it like this, where it looks like that proton is just falling off, but it's not just falling off, it's being removed by a base. Problem is, there are a lot of candidates for what that base could be. It could be the alkene, it could be HSO4 minus, it could be a water molecule, it could be a lot of stuff. So this is just a conventional way of writing a deprotonation step. But I want to make sure that you understand that that proton isn't just falling off of its own accord, a base is removing. Okay, so now let's do a more complicated acid catalyzed hydration mechanism. Practice in writing mechanisms. It's a 7-membered ring. Oh, those are so hard to draw. It's a 7-membered ring, and there's a vinyl tail up there and 2 methyls here. And what happened is H2O, acid and heat, and the product here is going to be that. Okay, so let's write a mechanism. Okay, first step is ho-hum, everything just normal. The double bond attacks undergoes protonation, and with Markovnikov regioselectivity, so that means we're going to want to put that proton on the carbon that is going to give the most stabilized carbocation. So in this case, that means a secondary ion. Okay, and so now, since we know that, okay, so there's the carbocation. It looks like the carbon skeleton has been rearranged from a 7-membered ring to a 6-membered ring. We know that there's a carbocation rearrangement is involved. All right, and so now there's the carbon 1. The neighboring carbon is carbon 2. Something bonded to carbon 2 is going to pull out of carbon 2 and plug into carbon 1. The charge is going to move from carbon 1 to carbon 2, and all of this is going to happen in such a way that we get a more stable carbocation from a less stable carbocation. So there's also carbon 2 on the right here, but if I take this positive charge off of 1 and move it over here to 2, I'm going from secondary to primary. That's no good, so I'm not even going to consider that. What I am going to consider is that I can move the charge from carbon 1 to carbon 2 by migrating this hydrogen. Oh dear, another 7-membered ring. And this rearrangement makes a whole lot of sense because I'm going from a secondary ion to a tertiary ion. Now that ring is not a nice 6-membered ring, so there's a little bit of strain in it, but not so much to make this rearrangement prohibitive. Okay, now all hell is going to break loose because now I have to scale this 7-membered ring down to a 6-membered ring. So it's going to be another carbocation rearrangement. So there's carbon 1, there's carbon 2, there's carbon 2, there's carbon 2. Something bonded to carbon 2, and there's a whole lot of carbon 2s on this. Something bonded to carbon 2 is going to pull out of carbon 2 and plug into carbon 1. The charge is going to move from carbon 1 to carbon 2, but we're going to get a more stable ion from a less stable ion. And the way you figure out what migrated is just by process of elimination. You have to consider all of the possibilities and what is it that is going to give you the observed product. Okay, so I want to ask you that in the chat. I see 3 carbon 2s. Tell me in the chat. Something bonded to carbon 2 is going to pull out of carbon 2 and plug into carbon 1. Tell me which carbon 2 is involved in the rearrangement. Is it going to be the carbon 2 on the left, the carbon 2 on the right, or the carbon 2 down at the bottom? Look where we are. Look at the product. What something is pulling out of carbon 2, out of which carbon 2 is something pulling out? Oh yeah, the bottom one. Good, everybody. And I need to come up with a more stable carbocation and something that is going to give me a 6-membered ring. So by process of elimination, what I figured out is going to migrate is this dot, right? Something bonded to carbon 2, the dot, is going to pull out of carbon 2 and plug into carbon 1. So a 7-membered ring for the last time. There's the dot. It pulled out of carbon 2. It plugged into carbon 1. And the dot is no longer bonded to that carbon 2 on the bottom. That carbon 2 on the bottom is now that. And the charge moved from carbon 1 to carbon 2. All right, so that's a hideously ugly drawing. Let's fix it. 1, 2, 3, 4, 5, 6, and back again. This is the same as a 6-membered ring with an ethyl tail there and a fish tail over here. And we can understand this rearrangement in that we're going from a tertiary ion that has some strain in it, because that's a 7-membered ring, to a tertiary ion that has eliminated that strain and formed a more stable 6-membered ring. So let's just make a note of that. Tertiary, comma, but strained. And this guy here, this is tertiary, much less strain. We've gone from a 7-membered ring to a 6-membered ring. Okay, And so now we see that this rearrangement has given us the skeleton that we need. We can finish off this mechanism now. We need to put that OH group on there. Water attacks an intact water molecule. I have to keep saying that because the most common mistake people make with writing this mechanism is you think OH minus attacks. It does not. You have sulfuric acid in there. That's a strong acid. OH minus is a strong base. Strong acid and strong base cannot coexist. The intact water molecule attacks. To make this oxonium ion, and then there is a deprotonation. A base comes along and removes that proton, but what could that base be? Just like we saw before, it could be water, that could be a base. It could be whatever the counter ion of the acid was, that is a base. It could be the alkene picking off a proton. So we have all of those candidates. Instead of committing to one of them, we simply write minus OH minus and minus H plus and picture that proton falling off. So there's our mechanism. Okay, so want to take a short break now. But let's see, because my opportunities to read the chat are very limited because I have to walk across the classroom and I can't see my screen. Does anyone want to tell me anything here in the chat before we take a break? Any questions or anything about that? I can't respond to the chat as fast as I can because of this setup, which I hope is temporary. For variation 1 on halohydrons, yes? Is there more? Oh. Okay, if you have a question, shoot. Does 5 or 6 membered ring, let me anticipate the rest of your question, trump the desire to attack the More substituted carbon? It does, but that's graduate school. So as far as we're concerned, it's just the More substituted carbon that is attacked. You could, chemists diddle around with molecules all the time. There are all kinds of examples where the less substituted carbon is attacked because you can form a more thermodynamically stable system. That's graduate school. Anything more in the chat before I take my coffee break? Right, I can't read the chat because of the setup I have going on in here. Fishtail, when the carbon attack, why is that not a 4-membered carbon group? Okay, fishtail. So this fishtail here, why isn't it a 4-membered ring? Because this bond here between the dot and the carbon that has the 2 methyl groups, the dot pulled out of carbon 2. So the dot is no longer bonded to carbon 2. There's the dot. It used to be bonded to carbon 2, which was here. But the dot pulled out of carbon 2, plugged into carbon 1, which is there. So you wouldn't get a 4-membered ring. So does that help? Anything else in the chat? Okay, so my computer says 9:54. I'll be back at 10:05. Okay, hi everybody, we're back. Okay, so we just learned about oh dear, should have done that. Just learned about a reaction that is a way of making an alcohol from an alkene. And so now I want to talk about another way of making an alcohol from an alkene, and hydroboration, oxidation. All right, so now this is as I said, this is another way of making an alcohol from an alkene, but this is quite a bit more complicated than that acid catalyzed hydration that we just talked about. All right, the overall reaction here is we start with an alkene, and this reaction is a two-step process. The first step is the hydroboration step. And in that hydroboration step, the alkene reacts with this stuff called borane, BH3. Sometimes you also see B2H6. That's just the borane dimer, but it's all the same thing. Many times you'll see THF, tetrahydrofuran, in there as well. That's just the solvent. So that's the first step of hydroboration oxidation. This is the hydroboration step. And then the second step involves the reaction of aqueous alkaline hydrogen peroxide. So here we could use KOH or NaOH, some kind of, let's put NaOH, aqueous alkaline hydrogen peroxide. And what is going to happen here, that's the oxidation step, step 2, is that double bond is degraded to a single bond, and it looks like the elements, the atoms of water added across where the double bond used to be. Okay, bullet points for the reaction. All right, the new OH on the less substituted carbon of the original alkene. So that is very different from acid catalyzed hydration, where the OH ended up on the more substituted carbon. So this is nice because now we have a way of putting the OH group on the more substituted carbon or on the less substituted carbon. Another bullet point for this reaction is that the new OH and the new H on the less hindered side of the original carbon-carbon double bond. Another thing to keep in mind about this reaction is that it is a cis addition. In other words, the new OH and the new H both come in on dashes or both come in on wedges. They're both going to be on the front of the molecule or both on the back of the molecule, but that's going to happen. That's the cis addition. Okay, so the mechanism of this reaction is quite complicated, but we don't need to really know everything about the mechanism in order to do product prediction. And as we study this reaction, the important thing is its synthetic utility. What kinds of molecules can we make using hydroboration, oxidation, and what will they look like? I'm going to talk about the mechanism, but that's mostly for the record. All right, so let's try some product predictions, just using this information that we have here. All right, so remember, this is one of our favorite molecules. And let's say we subject this to hydroboration oxidation. So those would be the steps. First step is the hydroboration step with borane, BH3. Second step is this workup step with aqueous alkaline hydrogen peroxide. Let's draw the structure of the product where we're just looking at these bullet points here. Okay, the OH on the less substituted carbon. So that means we're going to get the new OH at the 6 o'clock position of the ring on the left. The OH and the H on the less hindered side. So that means that the new OH and the new H are both coming in on dashes because the front of the molecule is more sterically occluded than the back. And it is a cis addition. So the product here is going to be dash, 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 OH on the less hindered side of the original alkene, and new H on the less substituted carbon, and new H dash, dash, dash on the less substituted on the more substituted carbon and on the less sterically hindered side of the alkene, and we see it's a cis addition. So that would be the product that we would get. All right, so let's try another one. How about a chair? Yeah, how about a chair conformation? All right, so maybe we saw this molecule in an earlier lecture. It's one of our favorites. BH3, that's the first step. Second step, H2O2, H2O, and NaOH. Draw the structure of the product. I would like to see a nice chair conformation. Okay, so this carbon in the front here, that's the less substituted carbon. That's where the OH will be. This carbon in the back, that's the more substituted carbon. That's where the new H will be. Tell me about the new H on the carbon in the front. Is it going to be axial or equatorial? Tell me in the chat. New OH on the less substituted carbon and on the less hindered side of the original alkene. So tell me about that OH in the front. Is it going to be axial or is it going to be equatorial? Yes, it's going to be axial because the top of the molecule is more sterically difficult to approach than the bottom. So this is going to be new OH down here, axial. And tell me about the methyl group on the carbon in the back, right? We're going to get, tell me about that methyl group on the carbon in the back. Is it going to be axial or is it going to be equatorial? Right, that carbon in the back has a methyl group and a new hydrogen. Tell me about that methyl group on the carbon in the back. Is it going to be axial or is it going to be equatorial? The methyl group is going to be also axial. See, here we have two possibilities. We have the axial substituent and we have the equatorial substituent. One of our bullet points for this reaction was that it's a cis addition. So the new OH came in from the bottom the new H also has to come in from the bottom. So I can't put the new H in this axial position because that implies that the OH came in from the bottom and the H came in from the top. So the new H is there, and this axial group has, this axial substituent has the methyl group on it, right? So here we see the new OH and the new H have come in both from the bottom of the molecule, the less hindered side. Okay. So the mechanism here is pretty complicated. When you're studying this reaction, most important thing is the skill of product prediction, right? But I'm just presenting this mechanism for the record. Mechanism of the hydroboration step, right? That's the step one with the borane. Now, we don't think of hydrogen as an electronegative atom, but in fact, the hydrogen-boron bond of borane is polarized away from boron and toward hydrogen. On the periodic table is laid out by atomic number. It's not laid out by electronegativity. We have electronegativity trends on the periodic table, but the periodic table is not laid out by electronegativity. It's laid out by atomic number. And in fact, the electronegativity of hydrogen is higher than the electronegativity of boron. So that the hydrogen-boron bond, if we look at borane, BH3, the hydrogen end is actually relatively negative, and the boron end of this bond is relatively positive. So that when we have an alkene, and so I'm going to demonstrate with this alkene here. Right, we have a methyl group there, we have a hydrogen here and a hydrogen there. Borane orients itself relative to the alkene in such a way that the hydrogen in borane is fronting up against the carbon that is going to produce the more stable carbocation if a carbocation were involved in this mechanism, but it's not. So the borane orients itself. So this would be the best place for the carbocation. This is just a way of remembering how this orientation happens. And so the borane orients itself so that the hydrogen is fronting up against the carbon atom that would produce the better carbocation. And we get hydrogen. We have this very peculiar four-membered ring transition state. Try to draw it. Pretty strange looking beast here, this four-membered ring. That's the transition state for this step. There is no carbocation involved. And then the transition state collapses to a species that looks like this, where that hydrogen has been delivered to the more substituted carbon. Okay, so now this guy here, this intermediate, it still has more hydrogen to deliver. So this guy can deliver 2 more H's. right? Because that boron atom still has two more H's. And so that's exactly what happens, is that this guy is now functioning as a hydride transfer agent. So we have two more alkenes get involved, and we end up with an intermediate at this stage that is going to look like dash, 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 methyl, hydrogen. Oh, I keep pushing buttons here, and every time I push a button, I do something wrong. Three of these are stuck to that boron atom. So that this intermediate here, after it reacts with the first equivalent of alkene, can still transfer more hydrogens. And so that's what it does. And so this molecule, this intermediate is now very, very bulky. And so that explains why this is going to be a less hindered side addition, because as the first and then the second molecule of alkene get involved in the reaction, we're going to get a big, big intermediate, and now it's very bulky. It can only attack the less substituted side of the original alkene. Okay, so that's the mechanism of this hydroboration step. All right, next, let's look at the mechanism of the oxidation step. So here we have mechanism of the oxidation step. All right, hydrogen peroxide reacts with the hydroxide. So remember, we have aqueous alkaline hydrogen peroxide. So this is the hydrogen peroxide, and that's the hydroxide. And we have an acid-base reaction in which the OH minus removes a proton from the hydrogen peroxide. We have this peroxide anion plus water. Right, and so now this is a nucleophile. This attacks the boron. So how to picture that? All right, so I'm just demonstrating with this molecule here now. Right, so this is going to be an R. This is going to be an R, because remember that boron picked up three alkenes. And so this O minus attacks this boron. And so we get something that looks like this. And we believe in charge conservation, so that boron has to have a negative charge. And now something very strange happens, something that we don't see in really any other reaction besides this, and that is a rearrangement, but it's not a carbocation rearrangement. It's a rearrangement to an oxygen atom. So as I said, I'm just presenting this mechanism for the record. The most important thing that I would like for you to retain about this reaction is the skill of product prediction. So this bond collapses in here, kicks out OH minus. I guess I better go this way. OH minus goes away. I have another R there. So R B, R. This bond is gone here. And now we have this species. See what happened is that bond pulled out of boron, it plugged into the oxygen, and then that weak oxygen bond broke. So we have something that looks like that. And now the OH minus that was just created and we have in the reaction mixture, now this is going to attack this boron and break this bond off. So now we would have R2BROH plus O minus that. And now the water that is involved in this reaction comes in functioning as a proton source. And so that O minus is, that negative charge on that oxygen is quenched. And so there's our final product, which is the alcohol, right? And now these steps happen once again with this guy. So the end result is the formation of these three equivalents of alcohol from the alkene. Okay, so, you know, complicated mechanism. It has this rearrangement to an oxygen atom, which is something we don't see in many other reactions. So not really worth spending a whole lot of time on this mechanism. As I said, most important thing here is being able to predict products. Okay, so let's see, let's try, since that's the most important thing, how about let's try another product prediction problem. All right. Fish tail up there. Hydrogen down there. First step, BH3. Second step, H2O2, NaOH, and water. So draw the structure of the product and show all the dashing and wedging. Okay, so we have new OH on the less substituted carbon. That's going to be up here at 2 o'clock. And is it going to come in on a dash or is it going to come in on a wedge? It's going to come in on a dash because the front of this molecule is much more sterically hindered than the back. So we have the new OH over here, and this methyl, and we have the new H came in also from the back. That's going to be on a dash, but I don't need to draw it. I can communicate the fact that we have that new H on the more substituted carbon, and it came in from the back by simply wedging that pre-existing methyl group that got shoved to the front. Okay, so the hydroboration oxidation and the acid catalyzed hydration reactions are ways of making alcohols from alkenes, but it's nice that we can now, we know how to put OH where we want it on that pre-existing alkene. All right, so now let's move on to the next reaction, and that is osmolation. All right, so we just saw some reactions that put one OH group on a molecule. This is a reaction that is going to put two OHs on a molecule side by side. So the overall reaction is we have the carbon-carbon double bond, and this again is a two-step process. The first step involves reaction with osmium tetroxide. So if you look at the periodic table, you'll see osmium is way down there somewhere, osmium tetroxide. And then the second step is a workup step, and many, many different reagents can be used in the workup step, but the most traditional one is going to be sodium hydrogen sulfite. Sodium hydrogen sulfite, but other things have been tried. Another thing that is that can be used here would be dimethyl sulfide, but sulfides have horrendous odors, so usually that's, although this works pretty well, it's not our first choice. And what is going to happen here is that the carbon-carbon double bond is once again degraded to a single bond, and where the double bond used to be, we have two OHs now. So this is called a diol. This is called a vicinal. We saw that word in NMR, a vicinal diol. In other words, it's two OHs on neighboring carbons. Bullet points for the reaction here: the new OHs on the less hindered side of the original alkene, and the reaction is a cis addition, just like we saw with hydroboration oxidation. The two new OHs on the less hindered side of the alkene, both on dashes or both on wedges, or both new OHs came in from the top or they came in from the bottom, it's a cis addition. And this is largely explained by the mechanism of the reaction. Once again, just like with hydroboration oxidation, the osmolation mechanism is very complicated because it involves all kinds of oxidation states of osmium. Don't want to get into that. Just want to present a simplified version of the mechanism. But before we do that, how about let's try some product prediction. All right, so we start out with this guy, and let's use the osmium tetroxide and then sodium hydrogen sulfite. So draw the structure of the product. So what's going to happen here? The carbon-carbon double bond is going to be degraded to a single bond, and where the double bond used to be, you're going to get two OHs there. Right? Does this guy have a more hindered side or a less hindered side? Does this alkene have a more hindered side or a less hindered side? It does not. So the reagent can approach from the front or from the back with equal probability. So if we want to communicate that, we would say, okay, so now here the new OHs came in from the front. And now, once again, it's not wrong to put a dash here, a wedge here. It's just kind of meaningless because that's not a chirality center that was created. However, this guy over here, oh, he is a chirality center, so this wedge has meaning. Now we have either created the R or the S enantiomer. But since this alkene doesn't have a more hindered side or a less hindered side, we could also, must also keep in mind that we could have attack from the back. And once again, it's not wrong to put dashes over here on this OH group. It just doesn't mean anything because that's not a chirality center. But this guy over here, he is a chirality center. And so we see that with this particular alkene, what we've gotten here is enantiomers. All right, let's do another product prediction problem. What about, let's see, something maybe a little bit more complicated. How about, let's do a chair. Let's do a chair like this, and maybe put this guy up here, we like him. Maybe put the double bond up there and put a phenyl ring. Okay, first step, osmium tetroxide. Second step, sodium hydrogen sulfite. Okay, you see where that double bond is? That's going to go away, and I'm going to get two OHs where that double bond used to be. But tell me in the chat, are those two new OHs coming in on the left or on the right? Okay, and I see I have, how do you determine the more hindered side? Well, is there something in the way of the reagent, right? So we're offering this problem hoping to clarify how to determine the more hindered side and the less hindered side. So that double bond, we're going to get, that's going to become a single bond, and we're going to have OHs on those carbons that used to be double bond carbon. The question is, are those two new OHs going to be on the left or on the right? They're going to be on the right, because the approach of the reagent from the left is hindered by this phenyl group, right? This is a big bad benzene ring. The reagent can't come in from the left because this pH is in the way. It's easier to come in from the right. So when you're looking to see which side of the double bond is more hindered or less hindered, you're just asking yourself, is there something in the way of the reagent as it comes in from one side or on the other? So, yep, the two new OHs are going to come in from the right because the left is sterically occluded by that benzene ring. So we have OH that way, we have OH that way. Yes? Now this reaction, this osmolation reaction has been important in organic chemistry, especially this example here, which I forgot to mention, is that this is acreolin. This is something that comes out of petroleum, right? Like so many other stuff. But the osmolation of this acreolin produces this stuff. These are sugars. These are carbohydrates. These are sugars, right? A carbohydrate is a polyhydroxyaldehyde or ketone. And so this is a polyhydroxy means more than one OH group. This is a reaction that puts in two OH groups. A carbohydrate is a polyhydroxyaldehyde or ketone. So this is a polyhydroxyaldehyde. So this reaction has been used to create all kinds of carbohydrate sugar molecules from crude oil. It's also been used to create carbohydrates that are very rare in nature. Now we can make huge amounts in a laboratory using this reaction. It's also been used to create carbohydrates and sugars that are not found in nature at all, but maybe have desirable properties. Okay, so now let's briefly talk about the mechanism, but I want to point out that this is a simplified variation. I'm not going to go through all of the steps because that would be 20 minutes. And I would have some steps that we don't see in any other reaction. And that would have some steps that deal with the various oxidation states of osmium, which I don't want to get into. All right, so start out with our alkene. And the osmium tetroxide, the Lewis structure of that OSO4 looks like that. So it's an osmium atom that is double bonded to 4 oxygens. This is osmium in the +8 oxidation state. And if you look for osmium on the periodic table, you'll see it's way down here. It's huge. So this explains why this is an addition on the less hindered side of the alkene, because the OSO4 reagent has that gigantic osmium atom in it. It is finds it very difficult to approach the alkene from the more hindered side. That's why it goes to the less hindered side. And the first intermediate that we want to consider here is this formation of this so-called osmate ester. All right, so it's not important what it's called, but this is called an osmate ester. Okay, where we see now that why this is a cis addition, because these 2 oxygens here, they're going to become the OH oxygens, and they were delivered to the less hindered side of the alkene, and it's a cis addition because they both came in on the less hindered side. And now we have the workup of the second step. And so I think this is really all the detail we need about this mechanism. And so those OHs came in on the less hindered side because the reagent is huge. It's a cis addition because they were contributed by that osmium. Okay, next reaction. Really piling it on here. Another reaction whose mechanism we need not concern ourselves with, because that would be another 20 minutes looking at steps that we'll never see again. Ozonolysis. All right, so this is a reaction that involves ozone, and you know that ozone is a molecule that we're all familiar with. We know that ozone is very good way up there in the stratosphere, where it is shielding us from high energy UV, but it's very bad here at street level, where it is one of the worst pollutants coming out of the tailpipe of a car. Also, maybe if you've ever worked with laser printers, maybe you've detected a very funky smell when a laser printer is working. Well, what you're smelling there is ozone, because in a laser printer, there's a hot wire that, that is exposed to the atmosphere, and it reacts with the oxygen to form ozone. Oh my gosh, fresh air is killing me. I need a cigarette. So here's what's happening in this reaction is we start with the alkene, and it's a two-step reaction. First step is reaction with ozone, which is that O3. And then the second step, just like with osmolation, is essentially a workup step. And one of the things that we can do here is the reaction with zinc metal and some kind of acid. Usually use acetic acid or ethanoic acid, but we could also use nitric acid, and I've seen other reagents used here. First step, reaction with ozone. Second step, zinc and acid. And what this reaction does is it takes that carbon-carbon double bond and rips it apart into two carbon oxygen double bonds. So the carbon-carbon double bond is rendered asunder, and it's turned into two carbon oxygen double bonds with those oxygen atoms coming from the ozone. All right, another thing that we can do here is different workup conditions. React the alkene with ozone, and this time instead of zinc and acid, we use hydrogen peroxide, which was the same reagent that we saw with the hydroboration oxidation. This has a similar effect in that that carbon-carbon double bond is going to be split into two carbon oxygen double bonds. But the difference between this guy up here and this guy down here is if there is an alkene hydrogen present in the original alkene, then treatment with ozone and hydrogen peroxide will oxidize this alkene hydrogen off to an OH group by an extremely complicated mechanism, right? That we're not in any way to really, any position really to understand. This pathway, this is called solvolytic workup. This pathway is called oxidative workup with this hydrogen peroxide. So just to repeat, is that ozone takes the carbon-carbon double bond and turns it into two carbon oxygen double bonds. The difference between the solvolytic pathway and the oxidative pathway is if there's an alkene hydrogen present on the original alkene, that alkene hydrogen is oxidized off to become an OH group. Okay, so that's the overall reaction. Let's try some product prediction. All right, so what if we were to take, okay, something simple at the beginning here. What if we were to take that guy and first step, ozone, second step, zinc, and a carboxylic acid, right? So there's the acid. We get something over here, draw the structure of the product. But another thing we could do is ozone, first step, second step, hydrogen peroxide. Will we get the same thing or will we get something different? Okay, so what's going to happen up here is that the carbon-carbon double bond is converted into two carbon oxygen double bonds. See how I'm trying to write it in such a way, it's an ugly, ugly drawing, but see I'm trying to write it in a way where we see that carbon-carbon double bond got converted to two carbon oxygen double bonds. This methyl group survives here. There is a hydrogen here, but he survives the solvolytic workup. So, but down here with the oxidative workup, that carbon-carbon double bond is sundered into two carbon-oxygen double bonds. But in this case, we had an alkene hydrogen on the original alkene, and that is oxidized off to an OH group. Right, so this illustrates the difference between these two procedures. Okay, so let's try some more complicated problems. I have an alkene, C10H16, and I react that with ozone, and then with zinc and acid. This guy is the only organic product that is formed. Draw the structure of C6H, draw the structure of C10H16. Okay, so maybe tell me in the chat if you can, maybe describe what C10H16 is going to look like. All right, I take C10H16, ozonize it, and then use solvolytic workup. Cyclopentanone is the only organic product that is formed. What was the structure of C10H16? I know it's hard to describe, but maybe here in the chat you can. It's going to be two 5-membered rings bonded together with a carbon-carbon double bond. Exactly. C10H16, DOU equals 3. So that carbon-carbon double bond was ripped apart into two carbon-oxygen double bonds. But because of the symmetry of this molecule, this is the only product that was observed. Okay, let's try again, maybe something like this. C7H10, and this time ozone followed by hydrogen peroxide. The product here was this. Wedge, wedge, wedge. The product was that. Draw the structure of C7H10. So I'm looking at this molecule and I see 5, 6, 7. So all of the carbons are there. I see two carbon-oxygen double bonds, and there was no oxygen in the starting material. So I could draw, I mean, if I wanted to, it would be ugly and hideous, but maybe something like this. What does ozone do? It takes a carbon-carbon double bond, and it breaks it apart into two carbon-oxygen double bonds. So these two carbons here, where the carbon-oxygen double bond is, they used to be bonded together, H2O2, sorry about that. And this OH group, there must have been an alkene hydrogen there, and there must have been an alkene hydrogen there. Well, that's a hideously ugly and unrealistic picture because there are no rainbow bonds in organic chemistry like this, but that's what happened. This used to be a carbon-carbon double bond, and now it got ripped apart into two carbon-oxygen double bonds, and the alkene hydrogens that were originally there got oxidized off to an OH group. Okay, so that's hideously ugly, unrealistic. How about let's redraw this? Oh, this was another molecule that we love. That was this. Right, where this carbon-carbon double bond got ripped apart, we got a carboxylic acid group on one side, carboxylic acid group on the other side. They are cis to each other, and the 5-membered ring in here, that's this 1, 2, 3, 4, 5-membered ring affair in there. Okay, so going to stop now.